Welcome everybody within Europe. It's a large group of forecasters, colleague forecasters, scientists who will join this live webinar as part of a high impact weather online course. And I'm really positive about the amount of participants, you, who will follow this webinar. Okay, I will start. And yeah, it's, I think, a little bit of a comic picture to see myself talking in the form of a text balloon. Well, basically, I'm a forecaster and trainer at KNMI. I have to say I did a lot of forecasting work in the past for some 15 years. Basically as an aviation forecaster for the general aviation at KNMI. And nowadays I'm partly a trainer and I'm also partly involved in the so-called climate advice group. So we are a sort of intermediary between research in the topics of climate change and the stakeholders. So yeah, and in my job as a trainer, I will focus on meteorology. So you can see a list of modules I normally give: synoptic meteorology and conceptual models, satellite meteorology, radar and mesoscale meteorology, and yeah, all kinds of specific models for our KLM and Transavia partners at Schiphol Amsterdam International Airport. So you have to think about some meteorology modules about hazardous weather for the aviation. Okay, let's start with the module of this first webinar today, and that's all about ingredient-based forecasting. And some 50 years ago, so half a century ago, this methodology was used in the United States of America. And well, some 20 years ago, we started to use this methodology in Europe, in the Netherlands as well. And as you can see in this slide, it's merely based on some general physical properties of air, so to speak, and you can more or less summarize it by saying that you look at some specific ingredients, and when they come together, then anything is possible. And with anything, I especially refer to convection. And an important statement is that please do not make climatology-based statements like this just cannot happen here. There are a lot of examples in Europe, in Western Europe, but also in the Netherlands in the past, that forecasters were saying, well, this is just not possible. To give you one example, in the very past, the old forecasters at KNMI were thinking that supercells were not possible in Europe. Well, as you noticed, that the knowledge about supercells has increased, fortunately, over the last 20 years. So ingredient-based forecasting, and it's based on 3 ingredients. That's moisture, instability, and lift. And then as a sort of 4th factor, that's called shear, vertical wind shear. That's also important to add to those 3 ingredients to determine the mode in convection. But basically, we start talking about the 3 ingredients, and to give you the big advantage of using this methodology is that in the past, maybe some of you recognize that we used to look at indices like Radcliffe, like Boyden, like Showalter, but that does not give you the physical insight of where you are looking at. And with this methodology, you are able to look at some ingredients and at the same time understand what is going on. And that's really important nowadays in the age of short-term ensembles and in the modern age of artificial intelligence. And that's partly a danger for forecasters by losing the physical insight. So that's my main message and my main motivation to use this ingredient-based forecasting. Okay, in this slide, you are able to see a so-called convection forecast scheme. We use this scheme in our forecast offers, in our weather room at KNMI. And what you can see are basically 4 steps. In the first step, in the upper part of this image, you can see the 3 ingredients: moisture, instability, and lift. And then as a sort of second activation step, you have to look at wind shear. So you can look at hodographs and the amount of wind shear, as we will learn today, will determine the organization degree in convection. And basically, what is one of the main implications of vertical wind shear is that you have a sort of a differentiation between the updraft and the downdraft in a storm. That's the main result of having vertical wind shear in the atmosphere. And then as step 3 and 4, that's more in detail, that you look at weather phenomena. And in step 4, you look in detail to the contributions which will lead to wind gusts. And that's also very important. Also nowadays, with all the improved limited area model outputs, that you still need to think about the contributions that lead to wind gusts, because the high impact weather related to wind gust is quite high. And step 3 and 4 I will discuss that in the second webinar on May the 6th. So today we are concentrate on step 1, basically on step 1. So to discuss the moisture, instability, and lift. And the key goals is to help you and to help also others, so also scientists who are not working in the forecast office, to understand a little bit more about how to deal with summertime convection with the help of this method. And well, as you can see in this slide, I underline the 3rd bullet point, where I am saying to understand the physics behind this methodology. That's very important. That's also a very big motivation if you compare that with 20 years ago, when you only looked at some indices. Okay, well, this live webinar is part of a, as you noticed, as you already have seen, an online material, an online course, high impact weather course. So we talk about this methodology, we talk about wind shear. I show you in the material also how you can determine the mode of convection. And then as a sort of extension, you can also look at all kinds of radar signatures, and with the help of satellites, especially nowadays with MTG, so Meteosat 3rd generation, you can more or less look in more detail to the remote sensing information than 10 years ago. So that has improved a lot. And in the end, the main goal is that as a forecaster, you are able to more forecast with self-confidence hazardous weather. Well, to give you a short summary how we work. So this the online part consists of a few reading parts, examples, and a quiz. And today we are dealing with a teleconference, and on May the 6th there is a second webinar teleconference with a lot of examples and also some room for questions, and also the questions I will ask in also today in let's say 20 minutes from now. And it's a sort of multiple choice question. Okay, in the end of doing this online course, you have more experience and more skills in estimating the degree of organizations, the so-called mode of organization, and related to that also the hazardous weather. Okay, let's start with the basics. And I guess that most of you have already seen the basics. And in this example, you see a typical cumulus cloud, which develops into a cumulonimbus cloud in an atmosphere with less or no wind shear. And you can recognize that by seeing that, yeah, more or less the downdraft will influence the updraft. Especially in the dissipating stage, you can see there's no updraft left anymore. So that's an atmosphere with less vertical wind shear. But the interesting thing about convection, about the development of storms in the atmosphere, is that it is in practice not limited to a single cell, but as you already experienced in your own country, in your own forecast office, you have basically some 4 modes of convection, and you can see them visible in some nice photos, merely taken in the Netherlands. In the left image below, you can see the city of Utrecht. That's in the central part of the Netherlands. It's very nearby the KNMI in the build. And you can see, there's a number connected to it, number 3. It's part of the theory about the 4 types of modes in convection. And this is, as you probably will recognize, a linear mode. So that can be a multi-cell cluster in a linear mode. So that's basically in practice a squall line. Okay. The forecaster in practice, and that's also my experience in the past, that you rarely meet hazardous thunderstorms. So that's quite seldom. So what is important is not to do is to start your shift with chaos. So that means that you have some unfounded preconceptions, and you waste a lot of time in preparing your first analysis, etc., etc. So what you should do is, on the hand of, for instance, this methodology, this ingredient-based forecasting methodology, to have a much stronger diagnosis. And to especially search for the low probability, the high impact situations. And at KNMI, for instance, we have the responsibility to issue color orange or color red, as many of you have elsewhere in Europe. So that's really a large or high responsibility. So it's very important that you learn to think in scenarios. Well, what is interesting is that each convective situation differs from the one that appears before. So for each convective weather situation, you have to deal with sometimes a slightly different situation, and most of the time with a different situation. So to start with the methodology, again, we look at moisture, instability, and lift. And now I'm going to discuss in more detail the step number 1, and I start with moisture. And then in the course of time, I have some nice questions for you all, and I will ask you to answer that through the chat. So you can easily answer it by using the chat. And the ingredients, moisture, to start with, is the dependency is evaporation and advection. And then, as you can see, with instability and lift, we will come to that a little bit later. So to start with moisture, again, the dependency is more or less in most of the days in summertime, it's the diurnal variation. So the diurnal variation means you have a sort of transport of moisture, of water vapor towards the ground during night, And during the morning, you have the opposite. Then you have a transport of energy, but also water vapor from the soil, from the ground, into the atmosphere. So that's basically what determines your dew point temperature at 1.5 meter. Above that, you also have advection. And then you have to think about some subtle advection moments that can occur when, for instance, your low level flow is coming from a wooded area or from a lake or from a sea, and that can influence your dew point by a half a degree or 1 degree, and that can have large implications. So a shift, I will show you that in a few minutes, a shift of 1 degree can have a large impact on your sounding. Well, moisture, again, evaporation and advection. And evaporation, of course, depends on the cloudiness, as you understand. And the advection, again, and now written on this slide, then you have to look at your source area where your low level flow is coming from. And to show you sounding, the first sounding in this live webinar, you of course recognize that this boundary layer is extremely dry. You have to think about a typical sounding which occurs in the desert areas. So when you calculate the ceiling of a probable cumulus cloud, then you have a ceiling all the way up to 500 hectopascal. So that's of course not that's of course not happening in most of the areas in Europe. Sometimes I have to say with very dry air from the south, some areas, especially in the south and southeast of Europe, can have very dry boundary layers. So I will come to that in a little bit later on this morning. But first of all, I will pay some attention to instability. And instability, and I think most of you have experience with using CAPE. So the convective available potential energy is, of course, depending on the diurnal cycles in terms of radiative heating, but also, again, your moisture content change and some general processes that take place above the boundary layer. So in the mid and upper atmosphere, cold advection is a very good example, will also influence the amount of CAPE. And I will go in a little bit more detail later on. Here you can see the typical sounding, in which you can see, for instance, on a particular day in Wien, Vienna, in Austria, you can see a typical inversion with a blue surface that's called convective inhibition. So that's nothing more than the strength of an inversion. And in yellow, you can see the amount of CAPE. And what's also important in this module is that there are some reference levels, like the lifted condensation level, but also the level of free convection and equilibrium level, which in this case is just below the tropopause, just below the stratosphere, I have to say. A little bit of theory why CAPE is important. Without going in too much detail, CAPE is nothing more than the amount of buoyancy, positive buoyancy, air parcels have. So then you have to look at the temperature difference between the parcel and the environment. That's the most easy way in one sentence to explain what is CAPE. And out of CAPE, you can calculate vertical motion, as you can see in the image. But this is nothing more than a first estimate, and that first estimate is most of the time wrong. So you have nothing about this calculation, because with this calculation you do not take into account the entrainment, which can be very important, no water loading term, and no dynamic pressure perturbations. And that last term is the most difficult one, because as a forecaster, when you learn about meteorology, you start by looking at the synoptic scale, and then you learn that the atmosphere is in hydrostatic balance. But with convection, with the development of storms, there is no vertical or no hydrostatic balance. So that means there is no balance between the gravitational force and the upward force due to the vertical pressure gradient. So that vertical pressure gradient will experience large fluctuations. That's the main reason why on the mesoscale you have to look at specifically to the dynamic pressure perturbations at itself. Okay, the first question to you. Please take your time and I will introduce this question. You can see two soundings, A and B, and those two soundings consist of the same amount of cape, but with a different distribution. And which sounding produces the strongest updraft? Is that A or B? So please use the chat to fill in A or B. It's simple as that. The correct answer is sounding A. And that has to do with the fact that the amount of cape is built up in a layer that is more shallower than the layer in sounding B. And despite the fact that the amount of cape is the same, you can see in sounding A, for instance, that an air parcel will accelerate a bit more simply because of a larger temperature difference between the parcel itself and the environment. That's the red curve. So yeah, and there are some more processes in the background, like entrainment and water loading, which you also can take into account to determine in the end which air parcel will accelerate a lot more. But the most important one is the temperature difference between the parcel and the environment. Okay, the next question. Please make use of the chat again. And this question is like this. You have now an equal amount of cape, but please be careful. The moisture profile differs. And I give you one tip. It's a tricky question. It's really a tricky question, but I will ask you this question because I think it will lead to a lot of discussion, also a lot of stuff to think about. So which sounding produces the strongest updraft? Is that A or B? Okay, now I will give you the answer, and maybe it will surprise you, because the answer is that you cannot say which sounding produces the strongest updraft. It's unknown, because you can choose for A with a motivation, with an argument that you have a smaller entrainment effect, and a little bit of explanation, because it's really a discussion in many forecast offices. You can see a more or less saturated profile that starts from the top of the boundary layer, the convective layer, all the way up to the tropopause. And that means that you have quite a broad updraft. And on the edges, of course, you have some entrainment, but in the core of the updraft, with the cumulus cloud and the TCU and the CB forming, there is a relative low amount of entrainment. But on the other hand, you can choose for B, because B, in comparison with A, has less water loading. Water loading is a term that you have to take into account when there is a high precip intensity. And in the sounding B, what's typical is a dry mid-level layer, which means that the first cumulus towers will be relatively small, and then after a while, when there is enough ascent motion, the the height of the tower, cumulus tower, will grow. So then that effect will decrease. But in the first stage, those soundings will lead to some more entrainment, but less water loading. So it depends on how strong the different components are in the end to determine which netto updraft is the strongest. Okay, now something about the cape, and there are more or less three types of cape. That's the surface-based SB. The ML stands for mixed layer, and MU stands for most unstable. And how do I have to see that? To start with the most easiest one. And I'm sure that also most of you have seen this before. That's based on an air parcel which you will lift from the ground. And I hope you recognize that that is not possible at itself in this sounding, because you can see a rather strong inversion around 900 hectopascal. But to determine the surface-based cape, you merely draw a line through the dry adiabatic lapse rate and a mixing ratio from the start of the dew point, and then you end up with the condensation level, and then from there you go through the wet adiabatic line all the way up to the tropopause, and then the blue surface is more or less the amount of surface-based cape. You can also make use of the mixed layer cape, and you were able to see the change between surface-based and mixed layer. And the difference is by mixing your bottom 50 or 100 hectopascal, you more or less mix the layer whereby the distribution of water vapor will follow the mix ratio line. So that's a very often used method to determine a more representative amount of cape, which is less than the surface-based cape, as you probably see. And the latest one is the most unstable cape. Here you can see the example. And that's mostly used during nighttime or in the evening when there is a decoupling of the boundary layer with the free atmosphere. So what you do is to estimate a sort of air parcel which starts to rise just above the inversion. And that will lead to the most unstable cape, and that's the highest cape in the sounding. Okay, next question to you. You can see three soundings, and I want you in the chat to fill in which type of cape should you use to determine based on the three soundings, and that's this sequence. So I think it's obvious that you, in the first sounding on the left, you need to use the surface-based cape. The second one, maybe you had some doubt, but if you look at the dew point curve, I hope you can see my mouse. You can see the dew point curve in the lowest, 20 or 30 meters. You can see that there is you can see that it is not well mixed. So you can immediately recognize a not mixed layer by having a dew point curve that is not following the mixed ratio lines. So that means that you have to mix this layer. And well, I think it's obvious that on the right sounding you have quite a strong inversion, so that you need to use the most unstable cape, so that you end up with having an estimate of air parcels just above the inversion. So the next subject is quite important to show you that cape is very sensitive to small changes in temperature. And look at the sounding. When I add a small increase of temperature, you can see that it has a large influence on the amount of cape. The same counts for moisture. Look at the sounding. I increased the moisture a little bit, and you can see that the amount of cape is again a lot higher due to the increase of moisture. And when they both increase, so temperature and moisture, then you have your large um, increase in CAPE. And it also means that when you increase your temperature and your dew point, that you are able to erode, so to speak, your inversion. And you can see that the amount of convective inhibition will be lower when you increase or dew point or temperature or both. So that's very important. And there are some typical sin values. When you have a value sin is 0, then you have no inversion, of course. Then you have just free convection, just thermals. So you just have to look at soundings which occurs most of the time in the course of the morning and in the afternoon, when you have enough heating from below to bring up air parcels up in the atmosphere. But it will become a lot more difficult when you end up with having some convective inhibition values, and it's all expressed in joule per kilogram, because CAPE is also a form of energy, and sin is nothing more than the opposite sign of CAPE. So it's a sort of negative available potential energy, which you have to overcome by, for instance, diurnal heating to get an air parcel above your eroded inversion. And with strong values, convection is, of course, not depending on diurnal variation, but then you need some amount of lift. And I will come to that in a couple of minutes. So, typical sin values are mentioned in this slide, and typical CAPE values are, it depends on the time of the year, but it depends also on in the part of Europe where you are. In Scandinavia, the CAPE values are in general lower than in the Balkan areas, the Alpine regions, Germany, France, Spain, Italy, Greece, Turkey. They normally have much higher values of CAPE than in the more northern parts of Europe. And typical values in Central and Southern Europe during summertime convection is between 1500 and 3500 or even 4000 joule per kilogram. Okay, so that's basically moisture and instability. Now something about lift. And I show you some forcings, like, well, what's obvious is, of course, a front. What's also obvious for most of you are the upper air troughs, the jet streaks, and the topography or the orography. What's really difficult, and that's still a challenge also at KNMI, are the outflow boundaries. But also the low level jets, because they are very difficult for us as meteorologists to have a clue about the strength of and especially the spatial distribution of the strength of low level jets and outflow boundaries. That still needs some improvement in the next years to come. And what's also very difficult are the gravity waves. That's a very subtle process and cannot be seen all the time, but you can nowadays use some more remote sensing information to detect the gravity waves. Well, lift is nothing more than vertical motion due to a forcing, and there are different scales and orders of magnitudes. So on the synoptic scale, you talk about centimeters per second, and on the mesoscale, for instance, an order of 10 higher. So 100 higher, 20 meters per second, sorry. So that's a lot more than on the synoptic scale. And well, lift, which leads to a forcing, due to a forcing to vertical motion, is a mechanism, for instance, to overcome your inversion, to erode your inversion. And I will show you in a couple of minutes the implications of having ascent motion. And that's very important, because your your environment will be primed, will change, will be deformed. And that's also one of the difficult things to imagine when you are on shift and you look at soundings, and then ascent motion will come in, and what that will do with your sounding, with your environment. And also the mesoscale models, the limited area models, still have problems in calculating those exact amount of ascent motion. The most easy forcing in your daily practice in spring and summertime is your diurnal variation, so the radiative heating. It will become a little bit more fuzzy when you look at really forcings. And the challenge is to have a clue about the strength of those forcings. So in the lower atmosphere, you can think about front, thermal troughs, outflow boundaries, sea breeze fronts, the low level yet again, and the orography and the gravity waves. And in the upper air, you end up with looking at the main features like upper level troughs, jet streaks, the correct entrance, exit regions, but also with strong upper air vortices, it's important to look at potential vorticity anomalies. And again, gravity waves. So gravity waves is mentioned in the lower atmosphere, but also will occur in the mid and upper levels of the atmosphere. Well, the role of large-scale ascent, I will pay attention on the end of a few slides, because my experience is also when I give this theory into the classroom at KNMI that some coins will fall into your head. That's a Dutch expression. That means that you understand the theory behind ascent motion. And it's important to realize that deep moisture convection only occurs if your saturated partial, your moist partial, will be lifted above its level of free convection. I think most of you are familiar with the synoptic scale equation, in which you more or less can determine the two main contributions which will lead to ascent motion. And what you cannot see and what is left out are some other factors which are very important on the mesoscale, which also can lead to vertical motion. That's for instance friction, but also a diabatic term. So that's latent energy. But for now, it's important to recognize that upward vertical motion on the larger scale, that's very important, is maximized where you have cyclonic vorticity attraction, which has to increase with height, and temperature attraction, which has a local maximum. Insiders in this group, you can recognize that you look at a sort of Laplacian, so the second derivative on a pressure plane, and so that means that you look for a local maximum of temperature attraction. That's the right term. But what is really the role? Well, to start with, this is the traditional omega equation, and what you can see are basically two terms which will lead to ascent or descent motion. That's also possible, but we are concentrate merely on rising currents, so upward motion. It depends on cyclonic vorticity attraction, which increases with height, and some local temperature attraction. And well, what is important is to realize that large-scale ascent is in the order of centimeters per second, while on the mesoscale, when you look at ascent motion in a cumulus cloud or cumulonimbus cloud, then you talk about 10 or 20 meters per second. So that means that large-scale ascent is not the ascent in which you can follow an ascending parcel, because the residence time for large-scale motion, the residence time of a parcel is too short. So what is very important is that the large-scale asset motion is primarily responsible for priming your environment. So that means that asset motion produces destabilization, and that is very important to realize. So I will show you that in a minute how it works. So large-scale ascent is not a trigger for a storm, but it makes the environment suitable. And then, as a sort of second step, then air parcels are able to overcome the an inversion and to all the way move all the way up to the tropopause. And then you need, of course, phenomena like fronts, outflow boundaries, sea breeze fronts, which can lead to enough convergence to give rise to asset motion, but then on the mesoscale. And asset motion on the mesoscale is due to the positive buoyancy and due to the cape, of course, which will take over the role of asset motion. Well, I hope you can see in this slide that to lower the strength of your inversion, you can do that with on the hand of three mechanisms. That's the middle and the right part we already discussed. That means you can increase your dew point by moistening, and you can increase your temperature by heating. But the left image, it's saying lifting, and with lifting, you are able to do two things. That's when you lift your air layer, what is happening is that due to the lifting layer, cooling will take place. So your temperature curve will a little bit move to the left, while at the same time evaporation will take place. So there's more water vapor coming into the mid-atmosphere. So your dew point will move to the right. Well, in this case, in this slide, you can see a sort of corrected blue temperature curve in which you can nicely see the disappearance of your inversion. So lifting is a very effective mechanism for priming your atmosphere. And in this slide, you can see nicely as a sort of summary, a basic view of the convective ingredients. And let me check if my connection is still, yeah, I still have connection, sorry. I just want to check it, just to be sure. To again look at this slide, you can see in the left-hand side and in the middle part, again, moisture and instability. That has influence on cape and also influence on the strength of the inversion. And in green, you can see some text like synoptic advection and synoptic ascent. And that's the main process for priming your environment. And on the right-hand side, you can see the process that is responsible for triggering. And with triggering, I mean that you need some kind of convergence in the lower atmosphere to get the parcels to the level of free convection. So it's, I think, for your insight and for your general physical understanding, that this scheme helps you differentiating between the priming of the environment and in the end the triggering you need, of course, for having ascending parcels. So that, I think, it's quite a nice basic view of thinking about the convective ingredients. Well, for the next webinar, and in a minute, I will give rise for you to ask me questions. But for the next webinar on May the 6th, so in 5 weeks time from now, I will concentrate on wind shear, but also on modes of convection and the related weather phenomena. So we go in much more detail about, again, the role of vertical wind shear and the related weather phenomena like convective wind gust, heavy precip, hail, lightning, with a focus on the straight line winds, which will lead for most of you in Europe for most of the problems in your countries. So that's, I think, very important. So now I will go over to the, I will stop sharing. I will go over to the general platform and I will give you the opportunity to ask me.
Good morning. Thank you for this nice presentation. First of all, I want to know if the conditions that are triggering convection, is it only valid for the extratropical area, or is it also valid for the tropics? One. Two, in the last slide, you were talking that there was no influence of large scale, while WMO is talking about seamless forecast that is integrating now to the short range, the intraseasonal forecasting or parameters such as Madden-Julian oscillation and others. So which comment can you make based on that? Thank you.
Yeah, thank you very much for these very interesting questions. To start with your first question, if I understand you correctly, you asked me to say something about the difference between using this methodology in the tropics and using this methodology in, let's say, the mid-latitudes. Well, I can tell you that there is some difference between looking at convection in the tropics and looking at convection in the mid-latitudes, and that has to do with the fact that in the tropics, merely the organization degree, which will come to you on May the 6th when I discuss, of course, the role of vertical wind shear, is a little bit different because the Coriolis force in the tropics is very low. So the typical modes of convection works a little bit different in comparison with the mid-latitudes. But furthermore, if you look at Cape and also SIN, you look at the three ingredients, you more or less can use the same logic order in determining the chance or risk that convection will occur. And so that's the answer on the first question. And the second question is a very interesting one. If I understand you correctly again, I'm not totally 100% sure if I understand you correctly, but please correct me, is that with seamless forecasting, you more or less fills in the gap between the short term and let's say the medium or the seasonal term. And yeah, if you talk about convection, it's a little bit difficult when you enlarge your forecast period. So this type of methodology is especially working for the very short term. So I mean with that, for the day itself. And of course, you can look at the days ahead. And you can also look at seasonal forecast by looking at distribution of amounts of Cape. But you have to be very careful by using this methodology for the very long term, because it normally works only for a type of nowcasting. So I hope this answers your questions.
Yes, almost, because we know that regarding the second one, the MGO play a lot of force and the SST. So now, usually when you do, I'm from the tropics, so we look at, is it in the active phase or not? So then we use the procedure you show us for the now crossing towards very short range forecast. But it's just to have a look to know that if you are in active phase of convection or not, if it's not, there's no inhibition of convection or less convection in the next few days, so that it will help us in terms of the procedure you follow. And you're right, it cannot, I agree that it cannot be the same thing, because like in my area, we have some specific jet during the monsoon, like West Africa monsoon, that we call Africa easterly jet and tropical easterly jet. And most of the time, is in between those two jets that develop thunderstorm and squall line and propagate westward. Thank you.
Thank you very much. And there's one comment I want to add on this, and that's also, I think, interesting for the rest of the participants, that when you look at the tropics and the maiden Julian oscillation, where you were referring to, the MGO, that's very important, I realize now, for the seasonal forecasting. Why? Very shortly, the MGO, when you have a clue about the location of the heart of the MGO, you are able to distinguish between the large-scale ascent and the large-scale descent motions, because there's also a connected descent motion. So a few months ahead, nowadays, within the WMO, you are able to make a sort of general forecast where those descending and ascent motions connected to the MGO are located. So again, thank you for this interesting question.
Hello, everybody. Thank you for the valuable lecture. I think it is a good lecture. But my question is, I need more explanation about 3 types of escape. What is the difference between them? Thank you.
Yeah, it's a very good question again, a very logical question, because to give you the answer, it's like this. Those 3 types of cape, that's it's more or less, to start with, a sort of theoretical number, and when that theoretical amount of cape comes into practice is when an air parcel is able to make use of that cape. You have to see it like this. So it depends on how the sounding looks like. So is there a strong inversion or is there no inversion? If there is no inversion, then your air parcels from the ground will make use of that specific surface-based cape amount. So that's then the practice. But when there is an inversion, then the air parcel, when it can overcome the inversion by some circumstances like lift, then it will make use of a different form of cape, and that can be mixed layer or that can be most unstable. So in the start, it's a theoretical number, and then in the course of the day, for most of the weather situations in Europe, it will become more clear which type of cape will be used. So I hope this will answer your question.
Hi, good morning, and thanks for the presentation. I have a question, maybe, well, kind of little request also for the second appointment. And I'm talking about, I'm particularly interested in the thunderstorm in the Mediterranean area. And in autumn, we have a kind of a specific thunderstorm that are generating usually a lot of damages, that are this back building very stationary thunderstorm. So I guess in this case there is a strong connection. So it depends on the shear, but also on a strong connection also with the large scale. So will you say some words about this in the next appointment? That will be very interesting for our community. Thanks.
Yes, thank you. I will do that. And that's also interesting for the rest of this group. And why? Because in the next webinar, I of course will tell you something about vertical wind shear. But on the hand of determining the wind shear factor, you can more or less pinpoint the point relative to the thunderstorm where daughter cells will develop, where extra cells will develop. And backbuilding is nothing more than that on the opposite side of a moving thunderstorm, new cells will form. And backbuilding will give rise to the highest impact possible related to flooding. And the flooding, most of the time, is severe to extremely severe because backbuilding is more or less a nightmare for the communities. Because again, most of the severe flooding will take place during backbuilding because the cell itself will stay for hours on the same place. So thank you for this question and also for this question to pay some attention to it. So I will do that on May the 6th.
Okay, thanks.
Good afternoon, good evening, good morning, depending on where everyone is. The session has really been good. Just a quick one. Mine is based on about the correctness or the effectiveness of the sounding data, because what is the geographical location of the sounding data, the effectiveness of it, because sometimes maybe depending on the wind strength or the wind speed of the place where the balloon is being sent, it can at times maybe the sounding or the balloon can be blown away to a different location, and maybe the area where you stay or the place or the country where you are is a bit small in size. So the data which will eventually come might be, or the data which will of course bring it will be a bit different. So how really effective is it that you can use it in doing a forecasting? Thank you.
Yeah, thank you. Thank you again also to you, Vincent, for your question. I already saw your question in the chat. And that's also an important one to deal with and to give you the answer for actual soundings on a specific place, of course. It can make sense. That is to say, when you have a strong wind aloft, and that strong wind starts to occur, let's say 1 kilometer above the launching place, then the rest of the sounding can deviate largely from the location where you are making a forecast for. So that means that especially when you are sitting on an island and the balloon is moving over sea, then the rest of the sounding will not be representative for your location on the island. So that can be tricky. And to overcome that, because we have that discussion at KNMI as well, nowadays you can easily look at proc soundings. And proc soundings is a sort of first estimate made by the model, which you nowadays quite nicely can use. If you look at ECMWF 9 kilometer resolution, you can easily pick up the proc soundings for your area. So that's in addition to the real life soundings, the balloon information. So I hope I answer your questions.
Yes, good morning. I have just one quick question about convective inhibition. Could you tell me or explain if it is helping to get severe convection, if there is some form of convective inhibition, let's say like 5200, which allows you to build up some potential cape, whereas if the convective inhibition would be unavailable, your thermals quickly develop and then they are gone. So in other words, does convective inhibition being present help build potential dangerous cape situations where we make the assumption that the lift and the diurnal variation or whatever is available?
Yes, thank you, John, for this question. And you are pointing in the right direction. That is to say that indeed, if you have some kind of inversion, then you can imagine that you need to pump in more energy for overcoming that inversion. And when you have, in practice, when you have a combination of putting in more energy into the boundary layer, and then in combination with a lifting mechanism or a forcing, then you end up with having more energy which will be released from the boundary layer by overcoming the inversion into the mid-troposphere. And you're right, John, then you end up with having more cape. So it's also called a loaded gun profile that means that with convective inhibition, you need to pump in more energy, which will release with more convective available potential energy. So then much larger storms, more active storms can develop with a larger ascent motion. So thank you for this extra direction of thinking, John.
Hello. Also about the convection inhibition slide, I want to have a question. You said that when is between 1 and 30 is the sufficient one, and the values 30 to 100 is a strong one. Is it the other way around?
No, how lower the values of sin, how less strong, how weaker the inversion. So if you enlarge the amount of sin, then you have higher numbers, then your inversion is stronger. That's the way how you have to interpret that slide.
Yeah, but on the slide 35 is that not inversion is stronger, is the convection with strong lift. And I think it's the other way around.
Yeah, sorry, I do not exactly know what you mean. I think you refer to another slide, so not only the slide where I put the numbers of sin and then the complication, so the result of having some amount of sin, and in general, what also John was referring to, if you have a high amount of sin, then normally when you do not have a forcing, there is no convection possible. But when you have a forcing, then you can also with high. I think that's what you mean. I think when you have high values of sin together with the forcing, then you can indeed have convection in the end. So that's, I think, what you mean. That's maybe the confusion that took place. But I hope that I explain it to you.
Yes, thank you very much.
Yeah. Okay. When I look at the time, and again, I want to thank you all. It was a pleasure for me to give this webinar, and I hope to see you back on the second webinar on May the 6th. That's okay, and I will send Tomislav the presentation, of course, and that will be shared in the Moodle course. And I want to thank the audience for, I think, for some of you, I think a lot of information in a short time. So don't be afraid to go into don't be afraid to ask me questions by email. That's also possible. That's at KNMI. That's Rob rob.groenland@knmi.nl.